Hello. So in our second part of Unit 7, we're going to be spending our time working with titrations. Titrations will always involve a neutralization reaction, so we're starting off super simple here, looking at our basic neutralization reactions on page 2, where we have an Arrhenius acid and base. Anytime an Arrhenius acid and base react in a neutralization reaction, we're always going to produce our salt and water. Whenever the acid or the base or both is strong, that reaction will go to completion. So it doesn't matter if it's the acid or the base or both. If either one or both are strong, it's going to completion. If a reaction goes to completion, it is not an equilibrium reaction. Thus, we don't need to do RICE on our neutralization reactions if we have something strong involved. Acid-base titrations are going to involve these neutralization reactions. Generally, we're titrating to the equivalence point, and that equivalence point is where our moles of acid and base are stoichiometrically equal. So we've completely neutralized each other into just that salt and water. And that salt could be acidic, basic, or neutral, depending on if we had two strongs or strong-weak combination of acid and base in that titration. So in this video, we're only looking at monoprotic neutralization, which means we have one H plus and one OH minus. So these acid-base reactions are going to have a 1-to-1 stoichiometry between your acid and your base. There are two methods that we can use to solve for these types of problems. There's the stoichiometry method. In the stoichiometry method, we're just doing normal stoich. We get to moles, we use our mole-to-mole ratio from the balanced chemical equation, then we get to whatever else the problem asks for. This is going to be easiest, especially if our acid or base is given as a solid, meaning that the mass is given to us in grams. The second way is our shortcut way. So the shortcut way is going to be best when our acid and bases are both given as an aqueous solution. So we're given volumes and concentrations for both acid and base. That's going to be primarily what we see when we're working with titrations. That shortcut is MAVA equals MBVB. So that's the molarity of your acid times the volume of your acid is equal to the molarity of your base times the volume of your base. Couple important things about this equation here. For our volume, we can use liters or milliliters. It does not matter which, as long as you have the same unit on both sides. This equation is also not on the formula chart. So let's look at why this shortcut works. When we are at our equivalence point, when our acid and base have completely neutralized each other, the moles of H plus is equal to the moles of OH minus. Well, whenever our acid and our base are monoprotic, or we have the 1-hydroxide for our base, the moles of H plus is also going to equal the moles of acid, and similarly for our base, the moles of OH minus is going to equal the moles of base. Well, if we take the molarity of our acid times the volume of our acid, that's equal to moles, because molarity, MAVA, because of our molarity equation. We know that molarity is equal to moles over liters. So when we take our molarity times our volume, we get our moles. So molarity of acid times volume of acid will equal our moles of acid. Again, it's monoprotic, so that's also our moles of H plus. And the same thing on that base side. Molarity of our base times the volume of our base will equal our moles of base. Since it's monoprotic, that's also our moles of OH minus. So really, this MAVA equals MBVB equation is just showing us that moles of H plus equals moles of OH minus, which is always true at the equivalence point. So let's look at using both of these methods in some problems here. On number 1, we want to calculate the volume in milliliters given 5 molar HF needed to neutralize 6.2 grams of sodium hydroxide. Well, on this problem, our base is given as a solid. Its mass is in grams. We can't really plug in masses grams into our shortcut version. So this would be a case where using that stoich method is going to be better. For our stoich method, just like any stoichiometry, we start with our given, which is that 6.2 grams of sodium hydroxide. We need to get to moles, so we can use our mole to mole ratio, and then we can solve for our moles of acid that were needed. So that molar mass of NaOH is 39.998. Once we get our moles of base, we can find our moles of acid because we know it's a 1-to-1 mole ratio. I know it's a 1-to-1 mole ratio because my acid is monoprotic and my base just has that 1 hydroxide. We could also look at the balanced chemical reaction that's happening. That balanced chemical equation, we see HF plus NaOH yielding our water and NaF, and it's all balanced. Everything's at 1-to-1 mole ratio. So 1 mole of our base is required to neutralize 1 mole of our acid. Once we've gotten to our moles of acid, we have 2 different options you can take at this point. Well, I have my molarity. Molarity can be used as a conversion factor because molarity is moles per liter. So if we have a 5 molar solution, that means that we have 5 moles of HF per every 1 liter of that HF solution. Well, I can use that in my dimensional analysis here. 5 moles of HF is our 1 liter of the HF solution. I did want our volume in milliliters, so we would just have that one last step. 1 liter is 1,000 milliliters. Since we only get 2 sig figs here from that 6.2, that's going to be 31 milliliters of that HF solution. Let's look at our second option we could have done here if you don't like using that molarity as a conversion factor. If you don't like using molarity as a conversion factor, go ahead and stop at your moles of HF and we can solve for how many moles we have. If we keep those 2 sig figs, that's going to be 0.16 moles of HF. Well, now I can take my moles and molarity and go and plug it back into our molarity formula here. When we go and plug that in, we do our 0.16 divided by 5. That would give us 0.032 liters, which is equal to 32 milliliters, keeping our same sig figs. If you use the full exact number in the calculator here, the 0.155 something that you get, instead of rounding it to sig figs at your moles, you'll end up with a 31, so that's why they're a little bit different. Either way is technically correct. It's better to keep that full number from the calculator, though, to get the 31 milliliters. But again, just a couple different ways you can go about that last step of getting from moles to liters. So let's look at one more problem here, number 2. On number 2, we have a titration happening. We have 45.2 milliliters of HBr, and we're given its pH. We have 25 milliliters of the LiOH. We're looking for the concentration of the LiOH. Well, here we were given aqueous solutions in a titration, so the shortcut is going to work best. That shortcut being MAVA equals MBVB, which is setting our moles of acid equal to our moles of base. Well, this problem didn't give me the molarity of my acid. It gave us the volume of the acid. We had 45.2 milliliters. We're looking for the concentration or the molarity of the base, and we had 25 milliliters of it. We have to be able to find the molarity of that acid. Well, it gave us the pH of the acid. From our pH, we can find our H+. H plus is 10 to the negative pH power. So that gives us 0.034 molar. Remember, with our pH, we got 2 sig figs, so we're keeping 2 sig figs in our molarity here. Well, that's our H plus. That's not necessarily the HBr calculation. However, they are going to be equal. We need to remember that for our strong acids, the strong acid concentration is going to equal that H plus concentration. So now we can go and plug that acid molarity in, 0.034 there, and just do some algebra to solve for the molarity of our base. Keeping our 2 sig figs, we end up with 0.061 molar for that lithium hydroxide. So on page 3, you have some more practice with this monoprotic neutralization. You can use either method, whatever floats your boat. But that is all for today.